So in low dimensional spaces, so feature vectors that are not too long with plenty of training data, nearest neighbors works very well. Actually, we are likely to have enough nearby data points to get a good answer for any query that we have. But as the number of dimensions increases, we encounter a problem. The nearest neighbors in high dimensional spaces are usually not very near. So consider k nearest neighbors on a data set of n points uniformly distributed throughout the interior of an n-dimensional unit hypercube, for example. So if we define the k neighborhood of a point as the smallest hypercube that contains the k nearest neighbor, and if we assume that L is the average side length of a neighborhood, then essentially the volume of the neighborhood will be L to the power n, where n is the number of dimensions, right? So the more dimensions we have in our feature vector, the higher the volume of that cube where we have to look for neighbors. So we can say that on average, L to the power n, which is the volume of that cube, will be equal to k over big N, where n is the number of data points. So, for example, if we say we have, we're going to take 10 neighbors, k equals 10, and we have 1 million data point, and we use a feature vector of only 2 dimensions, then in that case, the average neighborhood has a distance of about 0.003. Okay, and a small fraction of a unit square. If you use 3 dimensions instead, then L will be 2%. Okay, so only 2% of the edge of one cube. However, if we keep increasing the dimensions of our feature vector, if we get to 17 dimension, which is not a lot, L then becomes half the edge length of the unit hypercube. And if we go all the way to 200 features or 200 dimensions, then we contain 94% of the cube. So this is a problem that's very well known, and it's called the curse of dimensionality. So another way to look at it is essentially using shells instead of cubes, but the general idea or the general conclusion is the same. As the number of dimensions in your feature vector increases, the number of neighbors increases a lot, and the search space becomes way bigger, and methods like k nearest neighbors don't work very well, or would take way too long to search the entire dimension space. So let's look then at some ways that people developed to speed up the search for neighbors in a higher dimensional space. So finding the nearest neighbor with some modifications to it. So the first modification we want to use is what we call locality sensitive hashing. So hash tables have the potential to provide a fast lookup throughout a high dimensional table. But how can we find nearest neighbors using a hash table? That's the question. So when hash codes rely on an exact match, then it would be the same problem, right? Because essentially, instead of looking for the nearest neighbor in the original feature space, you're looking at the nearest neighbor in the hashed codes which have the same dimension as original feature space. You haven't done anything. Even though hash codes randomly distributed values among the bins, but we want to have near points grouped together in the same bin. Now that would speed up the process if we were able somehow to map our entire data into bins where each bin contains data points that are near together. Then when a new data point comes in, we only have to look for neighbors within the bin of that data point. We don't have to survey the entire training set. So that's why we call it locality sensitive hash, because it's a hash that is focused on local bins. So even though we can't use hashes to solve nearest neighbor exactly, but with a smart use of randomized algorithm, we can find an approximate solution. So first we define the approximate near neighbors problem as such. Given a data set of example points and the query point xq, find with high probability an example point or points that are near xq. Okay, so you notice we introduced the concept of probability here. We're not looking for a deterministic set of neighbors. We're only looking for points that have a high probability of being in the neighborhood for that given query. So to be more accurate, we can say that we require that if there's a point xj that is within a radius r of that query, then with high probability the algorithm will find that point xj. So to solve approximate near neighbors, we'll need a hash function g of x that can map for us from the original feature space x to the new hash space. Now this feature function will have to have a property that for any 2 points xj and xj prime, the probability that they have the same hash is small if their distance is more than a certain number. Okay, so that's how then we're going to design our mapping function or our hashing function, is that to make sure that if 2 points have a high probability of having the same hash, this means that they have a high probability of being in the same neighborhood in the original feature space. Okay. Now we rely then on the intuition that if 2 points are close together in an n-dimensional space, then they will necessarily be close when projected down onto a one-dimensional space, a line. Okay. So in fact, what we're going to do is we're going to discretize the lines into bins, similar to building a histogram. You're going to define bins on that line, which we call hash buckets, so that with high probability, near points project down to the same bin. Points that are far away from each other will tend to project down into different bins. But there will always be a few projections that by chance project far apart points in the same bin. Of course, this is a probabilistic problem, so it's impossible to guarantee for with 100% precision that we will always have points that are near each other in the feature space to also have to be in the same bin. Okay, there will be some type of error, obviously. So the bin then for the point xq, which we're interested in, contains many, but not all the points that are near xq in the original feature space. Okay, and it might even contain some points that are far away. Okay, there's no 100% precision, as we said. So the idea is then to reduce the impact of these poorly mapped points is to create multiple random projections. So instead of one projection on one line, we're going to create multiple random projections and combine them. So in that case, we can pick L different random projections and create L different hash tables, G1 through GL, okay? And then when then enter all the examples into each hash table, then given a query point XP, we fetch the points that are in the same bin as XP from each one of these hash tables and union them together into a set of candidate points. Okay, we'll call that big C. And then we compute the actual distance to XQ for each one of these candidate points in C and return the K closest point. Now notice that the size of that candidate set C is going to be much smaller than if you just did regular K nearest neighbor in the original feature space. Okay, so you're going to have to evaluate a much smaller set of candidates to identify the closest points among them. Now with high probability, each of the points that are near to XQ will show up in at least one of the bins, because these randomization are independent from each other, so there's no reason why if we missed a point in one random mapping, we will miss it again in the other one. They're all independent. So with large real-world problems, for example, like finding the near neighbors in a data set of 13 million web pages using 512 dimensions, locality sensitive hashing needs to examine only a few thousand images out of 13 million to find the nearest neighbor. So you can see the amount of savings here. So our entire data set is 13 million web page. Normally, if we use regular K nearest neighbor, given a given query XQ, we would need to calculate 13 million distance, right, between our query and each one of these data points to find the nearest one. But using this approach, locality sensitive hashing, we reduce the number of function evaluations or distances we need to calculate from 13 million to just a few thousands, okay, which represents a huge speed up over the traditional K nearest neighbor. Okay, so that's let's stop this part here, and then I'll see you in the next part.